right, so today we're talking about dynamics and friction. So we have our purpose. We're talking about dynamics problems involving friction. So dynamics, as you know, is the unit we are currently working on. So we're going to go through most of this. We're not going to get through the whole lecture today. We will get through each of these in time. Okay. You said you're nervous? All right, so we are looking at the fact that friction is a force that opposes motion, and it is important to note that friction always is parallel to the surface. Always.
Yes. I forgot to put always on my vocab. Is that a problem?
It may or may not be. We'll see. It depends on the context of the problem. All right. So we are going to look at the fact that static friction is stationary.
Oh, yeah, that was just normal force.
Static friction is stationary. Your objects that are experiencing static friction are not moving. If your objects are not moving, what is their acceleration? Zero. Perfect. So we are going to look at the fact that static friction can take a number of different values, anywhere from 0 up into a maximum. That maximum is going to be that coefficient of friction multiplied by our normal force. Right? This is the formula. I will tell you that formula looks a little bit more complicated than you actually see it on your formula sheet. I will tell you that your formula sheet does use the same formula for both static friction and kinetic friction, and it looks like this. All right, we're looking at the magnitude of the frictional force is less than or equal to the coefficient of friction times the magnitude of our normal force. All right, actually, your formula sheet does this slightly differently. Your formula sheet calls it F sub n. All right, same thing. So your formula sheet may use F sub n. I always use just the capital N for normal force. Remember that. All right, so we can see this is the formula for your formula sheet. This one over here is how I like to write it, with the fact that the friction is this lowercase curly f. We have the mu, and then n is the normal force. Yes, Chandler?
So is the mu going to be given to us, or is it a constant?
It's a constant for certain materials that you're talking about. We will be asked to solve for it in actually today's example problems. But sometimes you'll be given it, or sometimes you'll be given enough information to find it, right? It is, like I said, a property of the materials themselves. So you'll see a different coefficient of friction for rubber and concrete than you will see for steel on steel, or wood on vinyl, or whatever. So they come specifically from the two materials you're rubbing past each other.
Also,
yes.
How do we solve for? I'm probably going to talk about it. Mm-hmm. Not equal signs and less than.
That's an excellent question. So when they are equal, we're looking at max values, in which case you can solve without any weird algebra happening. Yep. All right, any other questions?
Yes, how do you spell mu?
All right, so we're going to go ahead and do an example problem. We have a 0.54 kilogram book sitting on the surface of your desk. You are pushing on the book with a force meter, increasing your force slowly. As you do so, the book begins to slide. However, just before it begins to slide, we read it, and we see that it's 4.1 newtons. We want to know the coefficient of static friction. We know this is a dynamics problem. How do we start all dynamics problem?
With Newton's second law.
Before we get to Newton's second law.
Write down the data.
The writing down our data and draw the picture. All right? So we have a book sitting on the surface. It has forces acting on it. It's on Earth, so gravity. Gravity acts in the downward direction. So it's got a force of weight. It's not falling to the table's supporting it, so what else does it have? Normal force. Right? We're pushing on the book, so it has the force of a push. We can put it in either direction we want. We can put it to the right or to the left.
I like the right.
You want to go to the right? Okay.
Because then it'd be right.
And what's counteracting our push?
Friction.
The friction, the static friction. And it's going to be in the opposite direction. It's opposite the direction our book wants to move. Yes, Jim?
So from now on, within problems, unless it says, like, you don't have to worry about friction, do we always have
Yeah,
to,
you do have to.
do we always have to account for friction?
Yes.
And that's like ground friction and air friction?
No, no air friction. No air friction.
No air friction.
Air friction or air resistance is considered negligible in this class.
I see.
Yep. Negligible means to be ignored.
Yeah, so I know.
All right. So now that we have our diagram labeled, we're still missing one more thing. What am I missing?
Oh, wait. I mean, mass.
The X and Y.
The X and Y axis. I do need to go ahead and label which direction is positive.
I have a question. Why did you write diagram of F and S for the friction? Instead of static friction.
Mhm.
And that's how we wrote it.
That's how I like to write it. Yes.
Yeah, just-
You could, if you wanted, do the F friction static if you want, or the long version. I like the curly F with the S. The curly F tells me I'm dealing with friction, and the S tells me I'm dealing with static friction. Yep. All right. So we need to find the coefficient of static friction. I will go ahead and tell you that we're going to need to deal in both the X direction and the Y direction. Which one do we want to start with?
Y.
Why? Yeah, why?
We're going to do Y. Okay, we're going to do Y. It doesn't matter which we do first. We need to do both. It's the long run. So when we look at applying Newton's second law in the Y direction,
Why would you do the y direction if it's just pushing sideways?
the equation for friction is equal to mu times N. N is in what direction?
Or not the down direction.
It's in the Y direction. It's vertical. Yep. Our normal force is generally up. So, we already established the fact that our object, because we're dealing with static friction, our object is stationary. It's not moving. All right, so what's our acceleration?
0.
0. So now we're ready to go ahead and talk about what is actually going on the left-hand side. What are the sum of my actual forces?
We can just do the F push and the F.
We're in the Y direction, honey. Our normal force minus the force of our weight. Yep. So we're going to look at the fact that my normal force minus the force of my weight is equal to 0. So that tells me my normal force is equal to the force of my weight. As we know from the definition of weight, weight is equal to mass times gravity. So my normal force is equal to mass times gravity. Right? We're going to end up needing this in a moment, which is why I went ahead and left it in there. Any questions so far?
Why is it normal?
Yes.
force?
Oh, sorry. Chandler first, then Alejandro.
Okay.
Yes.
I thought that when there's the gravity and then there's the normal force, that they canceled out and it was like all good.
They're not an action-reaction pair, and they're not, I mean, technically speaking, they're canceling it out because the sum of the net forces is 0 because they're equal and opposite. But we do need to know that they are equal and opposite. All right. Yes, Alejandro.
Why is it normal force minus force?
Because of the direction. So normal force is up, so that's positive. We are then adding the force of weight, which is down. So plus negative weight is the same thing as plus, normal force minus weight. Yep.
So the friction is equal to mu times normal force, right?
Yes, this is the equation we already went over. Yes, Alan. He asked if friction was equal to mu times N.
Oh no, okay, so I always get confused why you put in the Newton's rate of force?
The normal force minus the force of weight. Yep.
So
Remember, if it's an n in an equation, it's a variable, and I'm talking about normal force.
Yeah.
If it's n attached to a number, then we're dealing with newtons.
And like, what does it, they just cancel out the two forces?
That's why that's why the acceleration is 0, is because they're equal and opposite.
Okay.
Now we're ready to go ahead and look at the sum of the forces in the x direction? Okay. When we look at the sum of the forces in the x direction, again, we know our object is stationary.
So no acceleration.
So no acceleration. So this term goes to 0. So we're looking at the fact that the sum of my forces in the x direction is equal to 0. Now we can take into account what are the actual forces in the x direction.
The F push and the static friction.
Right? The F push and the static friction. My push is in the positive direction based on how we set our equation up before. So that will be a positive force. My friction is in the negative direction. So that will be a negative force. So I have my F push minus my static friction is equal to 0. That then tells me my F push, helps if I can spell the word push, is equal to my static friction, right? Because we're specifically looking for the coefficient of friction, we're going to substitute in the formula for static friction, which we talked about up here. All right? So my F push is equal to mu s times my normal force. Remember, we established before that my normal force was equal to mg. So when I rearrange this equation for the coefficient of static friction, I see F push divided by my normal force, which was my weight, my mg. Now we have everything sort of situated for us to go ahead and plug and chug. Yep, our F push is the 4.1 newtons. And the mass of our object is 0.54 kilograms. And it's on Earth, so 9.8 meters per second squared. Yep.
What's the formula?
What's the formula for what? Oh, 1 newton is equal to 1 kilogram times meters per second squared. Which actually brings us to why the coefficient of friction is unitless. I have kilograms over meters per second squared kilograms times meters per second squared over kilograms times meters per second squared. My kilograms cancels, my meters per second squared cancels.
Does it matter if you write 0.5 or 0.54?
You should write 0.54. I did this exact same thing this morning. It's like your order of operations. Did you put your 0.54 times 9.8 in parentheses?
0.78.
No.
That sounds closer, but I'm not. Where'd my calculator go?
Is it 0.77?
Cool. We got enough consensus that I'm just going to go ahead and accept it. All right. 0.4. 0.54. Right in the problem. Right there.
You said, so that's the coefficient. That's the mu, it's the mu, the static friction.
Mhm. It will be. And in fact, so most of your quizzes, if you put the wrong unit next to a number or drop a unit, you actually get a point off. This one, if you put a unit when it's a unitless number, you get a point off. All right. So part B, if you push on the book with a force of 2.5 newtons, we want to know the magnitude and direction of the static friction. We do not have to do a single piece of math for this. All right? 2.5 newtons. How does that compare to my maximum amount of static friction?
Almost half.
Almost half. So it's smaller. It's less than my maximum static friction. so that I know that the amount of static friction my object that I can get out of the problem is only as much as I put in, as long as I'm less than my maximum. Right? If I'm above my maximum, I'm no longer dealing with static friction. It actually shifts to a different kind of friction, and we'll talk about that. But as long as it's below the maximum, what I put in is what I get out. I put in 2.5 newtons, I get out 2.5 newtons.
Of static friction.
Yep.
But don't we have to say like left or something? Because this is direction as well. Oh.
I apologize for my very messy handwriting. But it is going to be opposite the direction of push. If I push to the left, it's going to be to the right. If I push to the right, it'll be to the left.
Is that because we started off?
It's related.
Opposite the what?
The direction of the push.
Oh,
Right. And now we're talking about kinetic friction. This is when the friction between two objects when they slide past one another. The direction of this friction is, again, always parallel to the surface. Whether you're dealing with static friction or kinetic friction, the friction is always, always, always parallel to the surface. It is also opposite the velocity. Right? We will end up talking about a very, very minor exception to this. It has to do with rolling friction, all right, and how cars work. We see we have a slightly different equation here. We do have one set value for kinetic friction. Right? Our kinetic friction is equal to the coefficient of friction times our normal force. Right? And our coefficient of kinetic friction is, again, still a property of the two materials that you're actually rubbing together. Right? And it is still a unitless number. The only thing to consider is that, generally speaking, the coefficient of kinetic friction is less than the coefficient of static friction. We'll talk about why as we get further into this unit.